Prepare yourself for an unprecedented cosmic catastrophe. The red giant star Betelgeuse, perched on the edge of our galaxy, is warning everyone in the universe of impending danger. Astronomers have discovered something quite unnerving about this enormous celestial entity. Using the James Webb Space Telescope, renowned astronomer Brian Cox raises a serious alarm, questioning whether we might be about to experience a supernova explosion that will completely alter the night sky. One star in the vast fabric of the universe, where stars are born, grow, and die in spectacular ways, has recently drawn the attention and concern of both the general public and scientists. This star is Betelgeuse, a massive red supergiant prominently located in the constellation Orion. It is enormous in both size and age. Long mysterious due to its unusual reddish color and fluctuating brightness, curiosity about this celestial giant has increased recently. We are at the brink of a potentially historic event in the star's life cycle as we investigate the nature of Betelgeuse. But what can these modifications mean? Are we seeing the beginning of an unfathomably grand cosmic spectacle? Betelgeuse is a massive star that is roughly 764 times bigger than our Sun. Its enormous immensity is nearly unfathomable to humans. Imagine a star so massive that it would swallow up Mercury, Venus, Earth, and Mars in its embrace if it were to replace our Sun, extending its surface beyond Mars' orbit. This extraordinary size indicates Betelgeuse's position in the stellar life cycle. In addition to its physical characteristics, Betelgeuse is a red supergiant nearing the end of its life. This phase is marked by expansion and cooling after the star's core underwent a life of fusing hydrogen and helium. However, what about Betelgeuse's age? This star is relatively young in human terms, yet it is ancient in terms of stellar lifetimes with an estimated age of 8 to 8.5 million years. Millions of years of evolution have culminated in its current red supergiant phase, during which time it has undergone numerous dramatic changes and processes that have shaped it from a hot blue star to the red giant we see today. Nuclear fusion and gravity are two processes that propel stars like Betelgeuse through a life cycle of constant change. Another distinguishing feature of Betelgeuse at this stage is its characteristic reddish color. Its surface temperature is comparatively lower than that of other stars like our Sun, which gives it its red hue. Betelgeuse's cold surface records temperatures of roughly 3,500 Kelvin, compared to the Sun's surface temperature of approximately 5,500 Kelvin. Betelgeuse appears red because of the wavelengths of light it emits due to its lower temperature. This star's color, however, tells us much more than simply how it looks. It also reveals information about the activities going on inside its enormous gaseous expanse and its physical state. Betelgeuse's historical color shift adds to its enigmatic nature. Ancient Roman and Chinese texts suggest that Betelgeuse was yellow around 2,000 years ago. The first accounts of it being red came from Arabic academics only in the 9th century. Not only is this color change a minor detail in the history of astronomy, but it also provides insight into the star's evolutionary history. Another interesting feature of Betelgeuse is its fluctuating brightness. As a semi-regular variable star, its light varies on a periodic basis. For generations, astronomers and skywatchers have been captivated by this distinctive dance of luminosity. Betelgeuse typically travels through two cycles, one lasting 400 days and the other lasting roughly 5 years. According to Sir John Herschel's 1836 documentation, these cycles may have existed earlier in Aboriginal oral tales. However, Betelgeuse's irregularity, rather than just its fluctuating brightness, is what really makes it mysterious. Unlike many stars that exhibit a regular pattern of brightness and fading, Betelgeuse occasionally deviates from this pattern, suggesting intricate and poorly understood processes taking place within its massive structure. In a recent groundbreaking discovery, Betelgeuse unexpectedly and dramatically changed in appearance, an occurrence known as the Great Dimming, which attracted the attention of scientists and stargazers worldwide. One of the brightest stars in the sky and a main component of the Orion constellation, the red supergiant Betelgeuse started to strangely fade in late 2019. The star's fading was so severe that it started to lose brightness at a daily average of 0.01 magnitudes, and by February 2020, it reached its lowest brightness. Even amateur viewers could see that Betelgeuse, typically visible to the naked eye in light-polluted locations, had become noticeably fainter. The time paradox presents a challenge when attempting to keep an eye on Betelgeuse's activities. Because of the time it takes for light to reach us, when we gaze at a star like Betelgeuse, we are not viewing it as it is in the present but rather as it was in the past. In the case of Betelgeuse, the light we see today departed the star about 725 light-years away roughly 7 centuries ago. This temporal lag makes it difficult to forecast and track abrupt changes in its behavior. The Betelgeuse dimming incident acted as a reminder of the challenges that come with doing real-time astronomical observations, as well as the boundaries of our knowledge when it comes to handling the enormous cosmic scales and the temporal paradox they create. Associate Director of the Center for Astrophysics at Harvard and Smithsonian Andrea Dupree and her team kept a careful eye on the unfolding of Betelgeuse's cosmic drama. They examined the massive star using Hubble as part of a 3-year project to track changes in Betelgeuse's outer atmosphere. These observations provided a unique window into the dynamics of Betelgeuse, a variable star whose brightness fluctuates due to periodic expansions and contractions. Researchers were able to examine the layers above the star's surface, which were partially heated by the star's chaotic convection cells, thanks to Hubble's sensitivity to ultraviolet light. Additional examination of the Hubble spectra obtained at various intervals in 2019 and 2020 aided in quantifying the flow of material in Betelgeuse's outer atmosphere. The magnesium-2 lines in particular, which are suggestive of the star's atmospheric conditions, were the focus of the spectra. According to these observations, material was leaving the star's surface and entering its outer atmosphere at a speed of almost 200,000 miles per hour. Millions of kilometers eventually separated this hot, dense material from Betelgeuse, serving as the forerunner of the dust cloud that caused the star to fade over the course of the 3 months following the eruption. Dupree and her team calculated that roughly twice as much material from Betelgeuse's southern hemisphere was lost as usual. Given that Betelgeuse, like all stars, regularly loses mass, albeit at a rate substantially higher than that of our Sun, this mass loss was noteworthy. Astronomers debated whether this mass ejection's magnitude and the ensuing darkening indicated a possible precursor to a supernova explosion. The mystery is increased by Betelgeuse's closeness to Earth, roughly 725 light-years away. Any explosion of that kind would be visible from Earth and offer a unique chance to see a supernova up close. However, the question still stands: what does Betelgeuse's future hold? Is this dimming event a sign of a coming supernova or just a singular event in the lengthy and intricate life of the star? Numerous hypotheses have been proposed to account for this abrupt shift. One popular explanation suggests a stage in the supernova explosion process. Another common explanation is that our perspective was obscured by dust, possibly from the star itself. It was believed that the material Betelgeuse, like other red supergiants, sheds could create a dust cloud dense enough to block off light from the star. A third theory examined modifications to the star's photosphere or visible surface layer, which might have impacted its brightness. This enigma was solved through in-depth investigation employing a variety of observational techniques. The effective temperature of Betelgeuse decreased, as revealed by spectroscopic measurements, indicating that a sizable dark area on the star's surface may be the cause of the dimming. The fact that Betelgeuse's temperature decreased by at least 170 Kelvin at the time of the dimming, indicating major surface changes, confirmed this notion. Ultimately, the Hubble Space Telescope, humanity's space sentinel, provided the key to comprehending this peculiar occurrence. According to Hubble's measurements, a huge ejection of hot material into space is most likely what caused Betelgeuse to darken. This material created a dust cloud that covered part of the star's surface, decreasing the quantity of light Betelgeuse was able to send our way. It was thought that superhot plasma, which burst from a massive convection cell on the star's surface and traveled through its heated atmosphere to the star's cooler outer layers, created the dust cloud. Roughly 25% of the star's surface was darkened by a cloud created by the solidification of dust grains as the star cooled. Beginning in January 2019, Hubble's ultraviolet light spectroscopic observations were essential in assembling the sequence of events before Betelgeuse's darkening. In the months before the star's brightness decreased, these observations showed evidence of hot, dense material passing through the star's atmosphere. Several ground-based telescopes saw the star's brightness decline in December 2019, especially in its southern hemisphere, as it migrated outward and cooled. This material, which was initially brighter than the star's usual brightness, finally caused the creation of a dark cloud. The abrupt dimming of the star was thought to be caused by this outflowing material and the ensuing dark cloud. The ejection's enormous scale has put Betelgeuse in the public eye on an unprecedented level. An estimated 400 billion times the mass normally ejected in a typical coronal mass ejection was emitted by the star. This material, thought to have weighed several times as much as the Moon, was a major development for both Betelgeuse and our knowledge of stellar dynamics. However, what does Betelgeuse and supernova theories as a whole stand to gain from such a massive material ejection? The ramifications for supernova theories are significant. According to conventional wisdom, red supergiants like Betelgeuse shed mass prior to their catastrophic demise at a fairly constant rate. The magnitude of this ejection, however, casts doubt on this theory and points to a more erratic and tumultuous latter stage of existence for these stars. Could Betelgeuse be preparing for the ultimate show? A supernova explosion in a few thousand years? According to recent studies, the timing of such an event may occur sooner than previously believed, possibly in a matter of a few tens of years. Another crucial piece of the Betelgeuse jigsaw is the idea of bow shock. This enormous star produces a bow shock, similar to the wave produced by a moving ship's bow as it hurtles through space at a speed of about 67,000 miles per hour relative to the interstellar medium around it. This phenomenon, a stunning illustration of the star's dynamic character and its interaction with the cosmic environment, happens as the star's outer layers interact with the interstellar gases and dust. In addition to providing information about Betelgeuse's current state, research on this bow shock advances our knowledge of mass loss mechanisms and star evolution. But how has the star been acting lately? Betelgeuse, a massive star in the Milky Way, has been observed to cool and become less dense after an ejection event, leaving it in an unstable state even years later. This ongoing instability raises questions about the internal processes driving these changes and how they might culminate in the future. The mass loss rate of Betelgeuse is significantly higher than many other stars, hinting at a complex interplay of internal forces. The recent unprecedented mass ejection has shifted the conversation, hinting at a more imminent end than previously anticipated. Theorists now grapple with the implications of such massive material loss and what it means for the star's stability and future. However, another cosmic event, the supernova SN 2023X, has captured our attention and offered a vivid comparative study of a star's cataclysmic finale. The discovery of SN 2023X was a cosmic coup, with telescopes worldwide capturing the unfolding drama of this newborn supernova. The dense shell of gas enveloped the star, significantly impacting the escape of the shock wave from the star's center. Two possible scenarios could explain this dense circumstellar material. Either a strong, steady wind had been shedding material from the star before the explosion, or the star experienced random outbursts hurling material into space. Identifying the progenitor of SN 2023X has become a focal point of study. By studying the details of SN 2023X's explosion, including its progenitor's characteristics and the mechanisms leading up to its final detonation, astronomers can refine their models of stellar evolution and supernova mechanics. However, there is a consensus that Betelgeuse is likely to be the next supernova in the Milky Way, although this event might not happen for another 100,000 years. The star's instability and the potential for a supernova are significant questions for the astronomical community, as well as the potential for further exploration of the star's life cycle. Supernovae have historically provided valuable insights into stellar deaths, with the earliest recorded instance dating back to 85 CE. Since then, several significant supernovae have been recorded, including SN 1604, the brightest star ever to appear in our night sky, and SN 1054, which resulted in the formation of the Crab Nebula. The most recent supernova observed in the Milky Way was SN 1604, studied extensively by Johannes Kepler. More recently, supernova 1987A in the Large Magellanic Cloud was observed within hours of its light reaching Earth, marking the first supernova detected through neutrino emission and observed across every band of the electromagnetic spectrum. The most immediate and visible effect of a Betelgeuse supernova would be a spectacular light show in our night sky, briefly outshining the moon and being visible even during the day. This event would be a breathtaking celestial display, captivating astronomers and stargazers alike. However, its true significance lies in the scientific opportunities it presents. Supernovae, particularly those of massive stars like Betelgeuse, are cosmic laboratories that offer invaluable insights into the fundamental workings of the universe. One of the immediate benefits of observing a Betelgeuse supernova is the opportunity to witness the final stages of stellar evolution up close. When massive stars like Betelgeuse explode, they distribute elements forged within their cores, including heavy elements like iron, into space. This process is responsible for enriching the universe with the building blocks of planets, stars, and life itself. By studying the spectroscopic signatures and distribution of these elements in the aftermath of a supernova, scientists can gain a deeper understanding of how stars evolve, fuse elements, and contribute to the formation of new celestial bodies. An equally intriguing aspect of the event is the emission of neutrinos. These elusive subatomic particles, notoriously difficult to detect due to their rare interaction with matter, are produced in vast quantities in the intense environment of a supernova. Detecting and analyzing these neutrinos would be a momentous scientific achievement, potentially unlocking secrets about the universe's most extreme environments. Observing a Betelgeuse supernova could also have implications for our understanding of the universe's expansion and the enigmatic force known as dark energy. Given the vast distances between us, this is an unlikely possibility.